Okay, today we're going to be handling the basic definition of the Laplace transform. Okay, and basically in elementary calculus, you learned that you studied operations of differentiation and integration, and you recall this something similar to this, where you could take the derivative of this set, and then you can pull out the constant. If alpha and beta are constants, you could pull out the constant in front of the differentiation and just differentiate the function. Okay, so you have two separate functions here, f of x and g of x, and so you're just differentiating each individually. And then with integration, you also learned that you could pull the constant in front of the integration and then just do the integration on the functions themselves, and separately as they add together or subtract. Then that would be called a linear operation. Okay, so in other words, another version of a linear operation is if you multiply a function, a solution times a constant, that is also a solution. And if you take two solutions and add them together, you still have a third solution. So that you'll come across this linearity stuff quite often. Okay, so this is true for definite integration, where you have a definite integral. A to B limits are defined. Okay, and then you're just applying it through this group here. And in this section, though, with regard to the Laplace transform, we are interested particularly in indefinite integrals, such as you see here, going from 0 to infinity, okay, of a function of s and t, s and t, okay, where the s elements are considered as constants, and the t is what we're going to take the integral regard to. So, and this is the integrand, this section here. So the way we handle this is we don't go from 0 to infinity. We take the limit as b goes to infinity after we take care of the integration. So it's 0 to b of the function f s t dt. Okay, so like again, I repeat, the parameter s, which is held as a constant during integration. So if the limit in this equation exists, then the integral is convergent. Okay, so that's what we're gonna say here. You saw about convergence of power series and so on and so forth, but there's also when you're dealing with infinity, you don't know if you're going to get a solution that's convergent or not. So in this case, it converges to a solution. Okay, so the Laplace transform then is going to be starting here. Okay, this is the intro, and so we're talking about something that is going to transform a function into another function, which may be easier to work with, and that's what our goal is here. So the above linear operations, both differentiation and integration, transform a function into another expression. Okay, so just like when you take the derivative of x squared, it's 2x. The integral of x squared dx is x to the third over 3 plus c. Okay, this is transforming this into something else. Okay, so, well, the Laplace transform is going to do this. It's going to take a function which is an f of t. It's going to transform that function into a parameter of s. And inside that world of s, we can operate on it and then turn it back into a solution. Okay, and that's where we're going to be learning in the future. So there's a bunch of differential equations in which these problems in both physics and engineering, where this Laplace transform will come in very handy. Okay, so let's see the formal definition of the Laplace transform here is 7-1. let f of t be defined for t greater than or equal to 0. Then the Laplace transform, okay, which is denoted by this bracketed type squiggly bracket here. Okay, that's how we put whatever we're Laplacing, we put inside that bracket. It's a function of f of t, and it's going to be equal to the integral, like we mentioned, from 0 to infinity. Now we're going to apply this e to the minus st in front of whatever the ft is. So if you're given a function, and in our example in a moment, it's going to just be a constant. So f of t is just equal to 1. Okay, but regardless, you're going to multiply whatever you're Laplacing times this e to the minus st dt, and you're going to go from 0 to infinity. And as I mentioned previously, that's the equivalent to taking the limit as b approaches infinity, and then we're going from 0 to b. So we're going to take care of this integral, and then we're going to apply the limit, and what remains is the Laplace of that function. Okay, is said to be the Laplace transform of f provided the limit exists. Okay, so we're taking the Laplace, and as I mentioned, we're transforming a t function into an f of s. We're in this realm over here of f of s, is where we can operate on this over here and then transform it back in and then get a solution to differential equations. Okay, that's a little bit further down the line. So let's just take the Laplace of a constant in this first example. The Laplace of 1. Okay, so here f of t is equal to 1. And from the definition up top here, 7-1, I go and take the Laplace of 1 equals 0 to infinity e to the minus st of 1. Here's where the f of t goes, right there. Okay, dt. And then again, that means we're taking the limit as b approaches infinity of 0 to b e to the minus st of 1. And as I mentioned to you, s is treated as a constant in this process of integration. Okay, so I'm going to show you, if I take the derivative of e to the minus st, which is what we're taking the derivative of here, after we apply to 1, I get a minus s e to the minus st. Well, the problem with that is I have an s out front, a minus s out front, and like I said, that's equivalent to a constant. So therefore, I have to apply a minus 1s in front of it to compensate, so that when I take the integral, okay, doing the antiderivative, then this is going towards the derivative, this is going against the derivative. I have minus 1 over s e to the minus st, and that's my solution. And you see it here, minus e minus st to the power minus st power over s. Okay, and the limit as b approaches infinity, but from 0 to b. Okay, so t is 0 to t is b, which is really infinity. And I'm showing you, so this is the upper limit minus the lower. So up here it's infinity, right, minus the lower, which is at 0. But I'm showing you here that this minus infinity s really goes to 0, and I prove it. Minus 1s is 0.037, and minus 10s is 0.0045, okay? And then here I'm getting e to the minus infinity s goes to 0. So this whole thing here will ride to 0. All right, and then this is all you have left, and this becomes 1. As you know, anything raised to the 0 power is 1, and the minus and minus takes care of itself, so it's 1 over s, provided s is greater than 0, because you add an s in the denominator over here, and you have to watch the path at which this takes, and never should a denominator be 0. So therefore you have s is greater than 0. That's your answer. The Laplace of 1 is plus 1 over s, now in the s domain.